So in Canada and in the US, Australia, South America, fires are a very significant natural ecosystem. It's a very significant natural disturbance on our ecosystem. There have been results from various studies that have documented the impact of forest fires, but there remains still a need to characterize the impacts under climate change. The seasonal nature of wildfire ignitions have been documented in many parts of the world where fires are natural disturbance, and this seasonal nature is pretty much the same, maybe with a fairly different shape in the seasonality curve in Australia, in the south versus the north. How climate change may impact forest fire regime characteristics is a concern, especially in Canada, and particularly, I would say, in British Columbia, which is on the west coast of Canada, because of the sorts of funds that are allocated for monitoring fires and for fire suppression activities. It scales into the billions of funds. And recently, there have been some suggestions that we aren't going to be able, in Canada at least, to continue to suppress fires. We are going to have to make decisions on which fires need to burn, and how we make those decisions requires some understanding of impact. So the increasing temperatures could increase the number of ignitions or result in a longer fire season. These are what I would call the postulated impacts that have been determined by simulating from global climate models. Many of the studies forecast potential impacts on fire danger indices or characteristics of fire regime under various scenarios. So these are, I would say, based on various climate models, and using climate models then to simulate what might be possible. What we started to do about 3 or 4 years ago is a little bit of a different focus in that it is retrospective. What we would like to address is the question of whether there are any evidences of trends across years in historical reports of lightning-caused forest fires. So there are two main questions that I will talk about in this talk. So when I talk about fire risk, by the way, fire risk and risk refer to the probability of a fire day, a lightning fire day, which is a day, any day during which one or more lightning-caused forest fires are reported. So here are some maps, here are some trends in Ontario. The lightning-caused forest fires varies throughout the fire season. It typically begins about the beginning of April and ends about the end of October. And there are a variety of different kinds of peaks depending on climate, depending on the weather in any particular year, and depending on fuel moisture, especially that year and the year before. The two sorts of trends that we were interested in looking at is how has peak risk changed, and whether or not the fire season is starting earlier or ending later. The question of the early or late end of the fire season is one that was driven by a request from a provincial ministry in order to determine when fire resources should be on the ground. So during the winter in Canada, there are no firefighting resources available. These are assimilated or brought together in the spring, and the teams assemble, the equipment is pulled out, etc. And we had some major fires that occurred early in the spring before any of the equipment and resources had been brought together. So there was a serious discussion when one of these fires threatened a major population area that we need to think about the fact that the fire season is now being extended because of climate change, and we need to quantify that and make some decisions as to whether or not we should be assembling teams earlier and keeping them on longer. In fact, I will tell you that the work that was done here actually did lead to a policy change in Canada, a significant one that brought the fire teams in 2 weeks earlier, defines the fire season by the Forest Fires Prevention Act, as starting earlier and ending later. And I'll give you some indication about how we did these analyses in order to provide evidence that these changes need to be made on a policy level. A lot of the work that was done by the teams of students who investigated different aspects relate to what I will call generalized additive models. And generalized additive models have been used in many different ways in ecology. It reflects the fact that we really don't know whether or not an effect of a particular variable is a linear one. And we don't have a process model to define what the effect would be. So could we have a more flexible way of defining what effects are, both for covariate effects and for spatial effects? So early work in generalized additive models for ecology goes back a long ways. In the fire modeling environment, there's work on using two-dimensional generalized additive models for fitting spatial effects, and also for using generalized additive models for fitting covariate effects. And here is a particular paper that discusses using spatial and temporal effects, fire weather effects, and human effects to assess forest fire activity using generalized additive models. So for example, distance to nearest railway, as a predictor for forest fires, which is in the bottom plot. Do you see my mouse moving? So obviously the risk is very, very high as you're close to the railway, and then as you're far away from the railway, the risk becomes zero. So using a linear model will not work here, but obviously a piecewise linear would work just well. But a generalized additive model gives you a sense of where is a good starting point for fitting maybe more sophisticated models. The seasonality curve is a very simple one for forest fires. The forest fire risk is low in the spring. This is the week of the year, and also in the winter months it's predominantly zero. And then it rises to a peak in the middle. So this is like an additive model that's based on week of year as the variable. The area that I'm going to look at, so this is Ontario. Down here is the US. You guys are about here, I think. And McGill is over here. And I am down here near to Niagara Falls. And this is the area that we're looking at. It's an area that there's very little suppression done to it. So we don't have to worry too much about changing suppression activities when we're looking at long records of historical fire. So whenever you're looking at historical data, there are a number of things that change over time. You know, fire, if you're looking at temperature stations might change in their placement over time, and you have to worry whether or not there needs to be some scaling as you're looking at, 100 and 200 years of data. This particular region we looked at because it had been, it's relatively left alone. Very little suppression activity, and it's an area that has a lot of forest fires. So if you look at changes in seasonal trends over years in this particular area, you do see that here is a two-dimensional plot, and here it is looking at from the top down. And you might suspect that there is a widening of the curve of peak risks. And so the question is, how do you quantify that widening? What are the tools available to us to look to see whether or not we are starting earlier and ending later in the fire season? And here are all the curves looked at year by year. So a simple way to do this, and this was done by a master's project, so I will tell you that this whole change in policy for the Fire Prevention Act was done by 2 or 3 master's students. It wasn't PhD level work. And it was a fairly simple analysis that looked at if you fit a generalized additive model and you define a risk threshold as 0.05. So at what time of year does the curve cross the 0.05 threshold? So fitting a model and estimating this by inverse methods, as well as estimating confidence intervals by inverse methods, would give you an estimate of the start and end of the fire season in any particular year. And so here, let's look at the day of year and the start of the fire season. Albert Green was the master student who did this work. So the start of the fire season, there's the estimate, and there's a confidence interval obtained by the inverse method. And so there's a lot of variability here is one thing that you would notice. And here are some anomalies that you might want to look at to see, what particularly happened in that year. And then you might want to fit a trend to it, a simple trend to say, well, what's happening over time? Is the fire season starting earlier? And there is some evidence that the fire season is starting earlier here. And you can do the same for a variety of thresholds just to see, how does this change if I look at a different kind of threshold? If I define the start of the fire season by the risk, a fire risk exceeding the 1% threshold, I'm so sorry. Does it also show a trend or a 10% threshold? Does it also show a trend? And so this master student looked at a variety of scenarios as defined by the provincial governments, and they all showed a trend in having the fire season begin earlier and also having the fire season end later. And these trends were significant. So this is a two-stage analysis. The first stage is fitting the curve, and then the second stage is using the fitted curves and the estimates in order to do a trend. This was a simple analysis that was done that seemed convincing, and not to mention the serious fires. Statistical methods aren't all that are required to change policy. You also need some dramatic effects to happen, and this was being done at the same time as we had some major fires happening earlier in the season that threatened property quite severely. So the whole process of having this work done plus some major events lent evidence to say, okay, we needed to do something on the ground. And so the Fire Prevention Act was changed to officially define the fire season as starting earlier and ending later, only for Alberta, but not for Ontario. And we can, if you have a question about that, we can talk about that. The peak fire risk is also changing. So the median, there are some problems with looking at peak fire risk, though. The size of detection is also larger in earlier years, so that we have a better detection system in Canada. That is a confounding factor. And also, the model isn't as simple as I just showed you. The question of whether or not there's evidence of a trend across years needs to understand that there is a major complication here in the need to account for three dominant characteristics of fires. So in our fire records, we typically observe the seasonal behavior pattern that I showed you. But there are two other dominant patterns that cannot just be dismissed. One is that in a particular year, there'll just be very few events. So this is called a zero-heavy problem. So we have what we call a quiet year. There's no activity on the landscape, or very little activity on the landscape. In fact, you know it, you experience it. You try to go camping in a year, and it's just friggin' raining for the whole season. So the years where we have lots of rain happening, then we don't have fires happening. And then there is the other extreme where there are far more fires reported than usual, a very, very large number of fires, and those are years that draw a lot of attention to policymakers. And so we need to account for a GAM model, if you're using a GAM model, in a different kind of way. So this is a simple three-component GAM model that says that There are 3 different seasonality terms, you can call them. A seasonality term corresponding to a normal year, one corresponding to a year that's quiet, and that is really 0, and one corresponding to a year where we have extreme events. The trend we're trying to isolate here is one which could lead to a reduction in the number of zeros or an increase in the number of extremes or both effects. And so we've parameterized the model in order to make it easier to investigate the climate change effects here. So if both these, the numerator and denominator terms, change slowly, if we look at this particular ratio, it will lead to large joint effects and more power to determine them. So this now moves beyond a master student into a PhD student work. And so it involves hidden components. We don't know whether a particular year belongs to a seasonal, 0 heavy, or extreme. There are autoregressive effects, temporal effects that are spatially varying. It's a very large data problem. There are confounding effects with the fire detection changing. And there is also curve registration that needs to take place. And I'll talk a little bit about curve registration in a minute. So if I just look at some of the results that have been obtained here, the figure shows the changes over the study period. So remember, this is just one small study area. The changes in the component-specific mixing probabilities. So how are the mixing probabilities changing over time? And it shows a strong decline in the probability that the system is in the 0 heavy component. So this decline is dropping from almost 38% in 1963 to about 26% in 2009. The decrease in the 0 heavy behavior is dominated by a shift in the likelihood of the extreme component being much higher over time. So from a change of almost doubling in the likelihood of the extreme component in a particular year. Let me show you the seasonality curves. So the seasonality curves here, the seasonal behavior for the normal component is as expected. For the 0 component, it's just 0. The extreme component is really just 2 values. It's essentially 2 values. You have nothing happening on the landscape at the start of the season, but as soon as the season starts, you have a particular probability or a strong probability of a fire occurring. So in these particular years, it's almost 1 here. The seasonality component says you're going to have fire on the landscape every day in the year. That's what this particular the particular model estimated. So the extreme years are very extreme. Nothing happening at the start of the season, but as soon as the season starts, then you're having fire activity constantly. So the model seems to fit the data reasonably well. This examines the goodness of fit by comparing observed counts versus expected under the model for these 2 components. The observed trends in the weekly proportion of fire days are weighted by their respective probabilities of membership in either the seasonal component or the extreme component. I should tell you that there was a particular year that needed to be removed from the analysis, and I failed to say that, and that year had a dramatically outlying effect in this particular curve here. And I'll actually show you that year as we move along in the talk. So this is now looking at the zeros. So this is looking at the probability, the seasonality component, the extreme component, and now this is looking at the zeros. The line is the expected number of zeros from the zero-heavy component, and the points are the empirical number of excess zeros. The zero component has a fair bit more variability in terms of goodness of fit than the other two components, as you see here. So we also wanted to test for trend, and as I said, the test for trend says that we have a higher number of extremes happening versus normal. The p-value said it was, in fact, just marginally significant, and we wondered about that. We wanted to say, you know, what are the right sorts of tests that need to be done here? And I'm going to show you a power curve in a minute to discuss what sorts of data, how much data do you need in order to be able to do these tests with any kind of confidence. Here is a plot of the overall curve. So temporal changes in the historical fire risk, looking at it by amalgamating all three components. And I mean, you can see just from the curve here the widening in the peak that's being estimated by the model. So these are the summary, and I don't think I need to say it again. You know, Alberta is suffering, Ontario doesn't seem to be. Peak lightning cause activity is increasing in one particular part of Ontario's forests, and there are certainly trends in the historical data. So one of the things that we were interested in is trying to determine you know, what do you need? How much data do you need in order to be able to detect a trend? We hadn't seen that in the literature previously. Most individuals would take some data and look at it. Being a biostatistician, power seemed really important. And so the question we asked is, you know, how many, now the sample size is not so much how big a space you use. The sample size is how long do we have to wait before we can determine that there's a change happening. So the question is, how many years of data? If there's a change happening, how many years of data do we need to have in order to say with confidence that this trend is significant? And so we looked at three different kinds of tests, permutation tests, wall test, and a score test. The permutation test really is a non-parametric method. What we do is, in order to repeat this analysis over years, we just do blocks by years. Excuse me. We do blocks of data by year. So we sample blocks of a year's worth of data in order to create 40, 50, 60, 70 years worth of data using the trends that are evident over time in the fitted models. And you can see we have about 45 years worth of data right now, and the power is terrible. You know, it looks like, you know, we're going to have to suffer for another, I don't know, 15 years before we have power at, you know, a level that's going to be convincing to individuals who are worried that climate change actually isn't happening. So in the forest fire context, in this particular analysis, we weren't able to say that we have high power in determining an effect. You know, you have to, it is insufficient to say that you have to wait another 15 years, because you also have to think about what's going to remain on the landscape to burn in 15 years, and if we're going to have anything at all, especially if fire suppression activity isn't happening. So it's a trade-off between what kind of power do you need and what's the impact to the earth that needs to be considered, and that's right now in the hands of the policymakers. We also tried to connect the results to climate anomalies. As you know, we wanted to really just look at historical data, not dream up climate models and say, okay, what do we expect to happen? But we thought it was important to make a link here. Fire ignition risk is widely understood to be influenced by a number of different factors. Maybe two of these are important ones are weather. I would say the two main environmental variables that have shown to have a major physical link to increase in ignitions are average seasonal air temperature and then moisture. And so I'm going to show you the plots relating to, I guess this is a correlation analysis relating to the each of these two. So air temperature has been found to be correlated with area burned, and so air temperature obviously influences the drying of the forest. So this particular plot, we looked at fire weather streams and created the average temperature anomaly in a particular year, and estimated also from the fitted model the posterior probability of membership in the extreme component. And there was a strong relationship between the average temperature anomaly and the posterior probability of extreme membership. So this trend here, I'm just highlighting it by a simple linear regression, but really we haven't done any sophisticated analyses on this yet. And the same for the second environmental variable that's really important in forest fires, which is the it's called the Duff moisture content, which is the moisture content just below the surface level. So it's how you could think of it about how moist is the soil, the top layer of soil. And again, there's a strong relationship between the two. So this is now building into an analysis that looks at the whole province, and now we have seasonality curves for the regular season. So extreme seems to be about the same for all areas, and zero obviously is the same for all areas, but the middle seasonality curve is not the same. The component that measures the average, an average sort of season. And so in order to do this analysis, now you need spatial methods that account for the fact that the season is starting differently from north to south as you go. This is a very big change in latitude, and also that the seasonality curves are very different. So you need a way to first off register the curves, so make them all start at the same time. In other words, shrink the time scale so that they are all approximately on the same time scale. In terms of when the fire season starts, south versus north, and then give some flexibility to the different kinds of shapes that you see in different regions. So it's a spatial analysis that's also based on spatial regression coefficients, and so these have been done as well. So now we're trying to build a bigger model. Finally, the very big model would say, okay, this is all well and good. You've shown that there's some effects, and in fact, you don't have a lot of power with them, but can we now try to make a climate fire link? And that's the step that we're at right now. And I'll just show you the black box that's developing this. Each of these requires a particular analysis that's very similar to the kind of analysis that I've shown you. It needs to account for space, needs to account for mixtures, needs to account for hidden elements. So each of these lines has a different, let's say, group of people looking at it, and a different kind of student. A master's student or a PhD student, and the emphasis now is to try to look at a process model that brings together statistical empirical techniques with the forest scientists' process analysis of how all these things are connected in order to make the climate fire linkages. And that's the stage that this particular project is at now in building a more complex model. And with this, then, you will also get increased power. And many of you will have recognized that the definition of the variable that I use will certainly give me very low power. Just looking at whether or not there's a fire on the landscape in a particular day just completely ignores the fact that some days you have lots of fires and some days you don't. And that's a massive loss to take a count variable and reduce it to a binary variable. So all of these things now are being considered. I don't know what Lou wants to do. How much more time do I have? I have some discussions of problems of interest that have dominated the literature. So fire modeling details, for example, on how to, this is work that's been done by David Brillinger. Basically, he takes the globe and divides the globe up into little squares. And then from these little squares, so it's a voxel, a space-time voxel. And in these little squares, he counts the number of fires and then analyzes the count of the number of fires in that particular square or cube, I guess, and how it relates to a lot of things. So how it relates to various different kinds of covariates that are in those particular voxels, space-time voxels. It's a very nice analysis, and it's a very simple one. But it is, let me say, data intensive. You need to be able to very carefully obtain relevant data in these space-time voxels and understand how they're related to each other. There's a lot of work done on rate of spread models. So this is a process model that's in the big black box that I was talking about just a couple minutes ago. And so some of the members of my community prefer to use empirical models, and some prefer to use physical models, and some a mixture of the two. The physical models are based on physical and chemical principles, heat transfer example, and there are at least 30 empirical and 40 physical models. And what we're trying to do is to get the physicists and the chemists together with the statisticians to say, okay, well, I mean, at least validate your physical model with data rather than just deciding to employ it in a more complex analysis. And fire growth models have also been done by mathematicians, not statisticians. So really what it is you've got this, let's take, this is the last stage of a fire. You consider dropping a whole set of points on it, and then each of these points is going to move in another direction for one time step. So it is a discrete model that the mathematicians have built up here. And how far it goes in a particular direction, each point depends on all the factors around it. So what's the wind speed in that direction? What's the temperature, etc.? What's the fuel in that particular cell? And then when you figure out where this particular point will move in the next time step, you join all the points up, and then now you have the convex hull that defines where the fire is after one time step. This is very important because right at the beginning of a fire, you have a helicopter flying into the fire and taking measurements on wind, on temperature, etc. They plug this into the model. And then what they do is they do simulation techniques. They say, okay, the fire incident commander will say, okay, let's drop a water bomber here and change the soil moisture. Or let's put some fans here and change the wind speed. How does that change the fire today? And then they'll run this model and see how it changes the fire. And then they do lots of different scenarios, and then they'll make a decision, okay, here's what we're going to do today. Usually they do that first thing in the morning, and then again about midday or in the afternoon to define how they're going to deploy the suppression activities. So this is part of a major tool that's used by fire incident commanders to manage. And this tool has a lot of problems in it in the way that it's been done. So one of the things we're trying to do is improve upon it. Let me see. So these tools can be used to generate risks for fire insurers, not just be used by fire incident commanders to determine what to do on a particular day. And so insurance companies have also been approaching us to say, you know, can you tell me what's the risk of a fire in these particular areas? And that I'm going to use in order to develop insurance portfolios for individuals who have lots of expensive housing there. So I talked about some of the problems, and this is one problem that is quite a serious one. So this is a particular day in Alberta in 1982. And the orange dots draw a line between the time the fire is reported to the time the fire is under control. And this is for lightning fires. The purple ones are for human-caused fires. So if you look at this particular day in Ontario, there was in Alberta, there was a storm that went through, and that storm just populated the landscape with over 100 fires. As I said, I've lost a lot of power in my analysis because all I'm looking at is whether or not there's a fire that happens on the landscape in a particular day, and use that to determine whether there are trends over time. No matter what you do, this is a serious problem. Even if you're looking at count data, these storms that move through and just pepper the landscape with lots of fires, it's really hard to work with that in a statistical modeling way that is effective. So I've talked about these multiple scales of space and time, different kinds of scale. Brillinger, by the way, has also looked at data the size of a flame, a candle flame. So he's played with fire both on the large landscape and also in terms of the small size. He was looking here in order to understand the process models that are developed by physicists on turbulent flow. Lou, I wanted to talk a little bit about practical suggestions for developing.
Charmaine, yes. Why don't you go ahead? We started a little bit late. Why don't you go ahead and do that, and then we'll see if we have some time for some questions before we take a little break.
Okay, so I mean, basically, this is. Let me just say, can I just skim and say that my own model to working has always been a collaborative model. I'm interested in working with biologists, scientists, health researchers in a team-based approach to analysis. I feel that this is very important. What I've done at the end here is I've talked about a few elements that I feel has helped me be successful and helped train my students, I would say, to be successful, because it's really my students their work is the one that has helped me advance policy in Canada. The first is focus. I'd say this is one of the most important characteristics, to be able to focus, to allow your creative energy to flow. It's critical, but it's not easy to come by. It often eludes us as we are bombarded by life. Just a second, I want you back here. How can I get you back? A moment. Have I stopped screen sharing?
Now we see you.
Okay, so we've got a lot of time management issues these days, and I'd say your generation is going to have it worse. Our generation has had a lot of difficulty figuring out how to just handle the bombardment of inboxes that's coming in. I think that it's going to escalate for you. And we are still struggling with how to manage things, and you've got information coming at you from many different ways, plus you've got lots of big data that you have to handle in terms of scientific analyses that's going to require a whole different way of working and thinking about things. The second thing is that I'd say challenge yourself right from the start. If you can position yourself well, if you broaden your perspective and learn new things. The usual strategy, I would say, post-PhD is to delve into issues and side connections to your PhD research. And I agree that this is a really good strategy. It helps you to move along very quickly, to get low-hanging fruit and reap them. It also helps you build on the connections that you've built and make them stronger. But I would also say use the tools that you've developed in order to make wider connections. Where else can you use the new methods that you've developed? How can you make connections to other areas where your research is going to be useful and make an impact? How can you open yourself up and open your scope up to new areas that are linked to your expertise? Use opportunities in order to develop this. I'd also say that it's important to aim for research with impact. Well, I mean, that's been my philosophy. It may not be yours. Maybe yours is that you have this particular study that you're interested in driving your passions. That's also important. If you're not passionate about what you do, you'll never make it a great success. But also look to see how your work can impact society. Are there ways that you can bring it forward? Try and try again. I mean, we worked with ministries and provincial governments, and often I know that my stuff goes in the recycling bin, but if you just keep going on it and pushing an agenda, then, I wouldn't say fortune smiles upon me when there is a major disaster with fire. That's not the right thing to say, but eventually you do get through that. Some things need to change. That also links in with publishing, rather than publishing smaller, isolated pieces of work, to weave them together to tell a bigger story and a complete story. Look at competing approaches. Take the time to do that and to make comparisons. Look at limitations. Be interested not just in the publication, but in the problem and its solution, how the solution benefits the world in which we live, how you can make an impact. I'd also say that it's really important to get to understand grant evaluations and grant processes. So grant proposals are really important. Very early with your career, I would say talk to colleagues who have served in the review system to get advice on proposals. Write lots of proposals. Take the time even now as you're a student to think about where can I write a proposal and send it off. I know it's not going to be successful, but get some experience. Take advantage of opportunities to review grant applications. If you can, ask your supervisor, are you writing a grant? Can I look a section of it? Can I help you with it? Is there something that I can do that will make it more successful? Some research that I can do? Get inside his grant proposal or her grant proposal to see what's being done, if there's a way that you can learn from it. Be bold, I would say, in trying to understand that mechanism, because it's getting tighter. And you need to be far more successful than your supervisor was. The world is growing. Seriously, there are more people on the earth, and there isn't enough money as there was for your supervisor. So you need to be smarter. Get your supervisor to help you with that. I wanted to say just a couple of remarks for the women on maternity and other leaves, just briefly. And men now take paternity leaves as well to help in child rearing. I would say careful planning in these leaves can really reap benefits. When my sons were born, I spent a lot of time with them for many, many months. My first son was born during graduate studies. And I cheated. What I did before my son was born is I prepared a whole bunch of extra material that I held back from my supervisor just to make him think that, I was a superwoman. So I didn't give it to him until after the birth and when I had recovered, and I was just struggling with life. But I had all this stuff all prepared, and so I was able to walk in and make it seem as though I was, really on top of things, cool and collected. Anyway, maybe that's not the way to work. Everybody's got to work on their own style, but try to plan ahead. Try to figure out what's going to work to suit you is all that I want to say there. Networking and mentorship are really invaluable. And look at the wonderful opportunity that Lou has given you here. It's invaluable for raising your profile, for developing a broader view, for finding out about opportunities that you may not know about. If you want to talk to me about Caribbean connections, the young man in the front, maybe I can help with that. It helps you build your professional profile. So use networking with internal and external stakeholders. Don't be afraid to network with external stakeholders. It's they tend to be not so receptive, and then you have to figure out how to give your 3-minute elevator speech that will convey your message in a short way that's going to reach them. And the only way that you're going to be good at that, I'd say, is by doing it. doing it many times, and then finally understanding how you're going to reach somebody who's working in an area that can really use your work and have an impact with it. I think that's all that I have to say in, be passionate about what you do and enjoy it.
Charmaine?
One of the beauties of statistical science and biology is that these are areas that are really important for the world right now. And you guys are in that field. So you are poised to have a major impact on the world.
Let's thank Charmaine very much.